Recording, and I'm sharing, and everything's good. Okay. Okay. So don't be mad. I'm handing out an assignment. There is one online as well. I know, how rude, right?
7 was online.
But this is 8.
Oh.
Oh no, I know. But it is, in my opinion, pretty reasonable. But there's some stuff that the Moodle quiz can't test you on. Especially because it's just like the highest grade at multiple choice, so. Not real. Okay. So this assignment, I will let you hand in as a group again. So if you want to work as a group, you're welcome to, but like I said, definitely manageable to just do it on your own, but if you want to work as a group, that's fine. I still want it on the handout that I gave you. There's 4 questions and nothing crazy. Most of which we've done in class an example of. So actually all of which. I wouldn't pick one if we haven't done an example of it. Okay, so you're allowed to hand it in as a group. I want it to be really nice and neat. So maybe try doing a draft first. I don't know. Go crazy. Only because the first page I found that it was a little bit tight for space, but so you'll need to plan your real estate accordingly. All right. Oh, I also posted a tiny assignment 7, which is a Moodle quiz. So let's just assignment number 7, which is a Moodle quiz, is, where did I put that little piece of paper, is due November 26th at 23:59, so basically midnight. And remember assignment number 6, which it seems like you guys have conquered already from who I've talked to. It's a Moodle quiz, but it is due November 21st. And I just make them all due at midnight or 11:59. It is due November 26th as well. Assignment number 8. Is on paper, and it is due November 26th at the beginning of class. Okay. You may submit as a group. Right. In fact, if you're working with other people, I want it handed in as a group. Voila. Good. Right, so if you're kind of working with people, working with other people, then you should probably just submit it as a group. So there's a group thing going on. Just get an assignment.
Susan birthday yesterday.
It was? That's 3 pieces of paper just for you.
Oh, I feel so sad.
Yeah. Congratulations. Okay. All right. So that's assignment central. I know, why so many assignments? Well, the Moodle assignments are kind of, yeah. They're, I mean, some questions make you think a little bit, but a lot of them are just kind of like, look at this and do this. And so they don't really go into detail. And on the final exam, you'll need to be able to do things like on the assignment, on the paper assignments. And so that's why I have to give you the paper assignments. But also, there's no test for this section, right? We're just heading straight into the final. And so I want you to have lots of work done so that you can have feedback. Okay. Any questions about assignment town? No. Then let's talk about the rest of the circular functions. We've talked about sine and cosine, right? But in section 10.4, we're talking about the circular functions. Tangent, secant, cosecant, or secant and cosecant, it doesn't matter, and cotangent. In fact, I even think I'm inconsistent in how I say it. It just depends on how it flows in the sentence. Anyways, it doesn't matter. On a good news side, once we finish today, there's only 2 more sections that we're doing, and it's the sine law and the cosine law, which are basically the Pythagorean theorem, but for non-right triangles, right? And so that should be pretty fun and pretty manageable. So there is an end in sight. You can do it. All right. So in total, there are 6 circular functions. It's like a record attendance day. 2, 4, 6, 8, 10, 12. Wow, it's pretty good. Did you guys have a talking to or something? Did you guys get in trouble with Allison? I didn't tell on you guys. So in total, there are 6 circular functions, and on the handout, we've got them listed. And in fact, we've kind of got them listed twice. I'll just copy them, and we can talk about them. Oi, it's huge. Okay. And so the circular functions, we've got sine and we've got cosine. We've already talked about sine and cosine as if they're the x and y coordinates of a point on the unit circle, right? And so what we can do is we can talk about the tangent, the secant, the cosecant, and the cotangent in terms of x and y, right? And so here we've got the tangent as y over x, right? But then in the next block, right, on your handout, and make sure everyone has a handout. Did you get a handout, Kelsey? Okay. So on your handout, the next kind of blurb just says this all over again, but in terms of sine and cosine, right? Where y is being replaced by the sine of theta and x is being replaced with the cos of theta. So this one is kind of obsolete, but it does bring it back to the x and y coordinates on the unit circle. So I guess I should write that. Of the 6 circular functions, only sine and cosine are defined for all angles of theta, right? Because the tangent, we've got the restriction that x can't be 0, right? We can never divide by 0. So as soon as we've got that fraction, we've got restrictions. And so, so of the 6 circular functions, you'll notice that only sine and cosine are defined for all angles of theta. Are defined for all angles theta. So we can rephrase the remaining angles in terms of sine and cosine. We can rephrase the remaining angles in terms of sine and cosine, which is Theorem 10.7 on your handout, which I'll just copy over. Copy that. So here we've got them rewritten in terms of sine and cosine, right? Just replacing x with cos and sine with y, or y with sine, words. And so, and then we've got restrictions on what our denominator can be, just like always, right? And so here, these are identities, right? Because they're going to be true regardless of the value of theta. But some of you will be pleased to know that these are the only identities that we'll handle. So these are called identities since they are relationships, are relationships which are true regardless of the value of theta. Relationships which are true regardless of the value of theta. So what happens is usually, just as like a kind of a rule of thumb for solving these problems, is if you've got a secant or a cosecant, you usually kind of transform it back in terms of sine and cosine, whereas tangent and cotangent, you're better off usually just leaving it in terms of tangent and cotangent. And so I'll just make a note of that here, but I guess you'll figure that out as you go. So in general, When solving equations involving secant and cosecant, when solving equations involving secant and cosecant, we usually convert back to sine and cosine. We usually convert back to sine and cosine. However, when solving for tangent, or cotangent, we usually stick with what we have. Usually stick with what we have. Yeah. For that reason, I gave you some values of tangent and cotangent on the handout, right? Just like we have for sine and cosine, right? Those kind of checking points. So I'm just going to grab that from the handout here. You'll notice, right, that we've got the same thetas as we did for sine and cosine, right? There's no reason to have different thetas. So over 6, over 4, over 3, and presumably, yeah, over 2. So since we know some common angles of tangent and cotangent, some common values, right? We can use them the same way that we do for sine and cosine, and that's why there's no real need to convert back to sine and cosine, or in terms of sine and cosine. We can combine this theorem, right? That secant is 1 over cos, and cosecant is 1 over sine, and tan is sine over cosine, and cotangent is cos over sine, right? We can combine those with the reference angles, the reference angle theorem from way back when, theorem 10.1, to get theorem 10.8. We can combine theorem 10.7 with the reference angle theorem, which is theorem 10.1, to get theorem 10.8, which is on your handout. Look at all that writing you don't have to do. So here, and there's nothing kind of crazy going on here. It's just saying that the sine of theta, well, if you've got a reference angle, then it could be plus or minus sine, right? And so same for all of these guys, right? If you've got a reference angle, then it's either going to be positive or negative, like we saw with sine and cosine, right? Depending on what quadrant we're in, the value is either going to be positive or negative, right? And so the same thing happens with the rest of them. as it says in the bottom there, oh, which one is getting an auto update? Great. So many moving parts. So where the choice of the plus minus depends on the quadrant in which the terminal side of theta lies, right? And so, and it's going to trace back to the values of sine and cosine. How about an example? Example. Find the exact values, so meaning no decimal places, just roots and pi's and whatever you've got, right? So find the exact values. The exact value of the following if it exists. Part A, we're going to find the cosecant of 7 pi over 4. And I'll write this big. So what we said was, okay, for cosecant, we're actually going to rewrite it in terms of sine and cosine, because we can find, well, so cosecant, remember, was back here, 1 over sine theta, as long as sine theta is not 0, right? So if you ended up with a sine theta, so if sine 7 pi over 4 is 0, right, then it doesn't exist. It will exist in our case, right? But so we've got 1 over sine theta. So this becomes 1 over sine 7 pi over 4. Hmm. 7 pi over 4, you've got your handouts handier than I do. Let's use this one. 7 pi over 4 puts us in the 4th quadrant, right? And so our x is root 2 over 2 and our y is negative root 2 over 2. And so our sine is our y value. And so we've got 1 over the negative square root of 2 over 2. This is technically a fraction over a fraction, right? And so I can flip and multiply. And so I've got 1 over 1 times negative 2 over root 2. Oops, that's not a root. Which if I multiply this out, I get negative 2 over root 2. And here I had a couple of questions yesterday about if you have root 2 over 2, how does that become 1 over root 2? I'm going to use the same trick here. I'm going to rewrite 2 as root 2 times root 2, right? Because it's root 2 squared. And so I get negative root 2 times root 2 over root 2. These two cancel. And so this answer is just going to be negative root 2. I'll just make a note here that on the Moodle assignment, Root 2 over 2 is not an option. But 1 over root 2 is an option. Right, if you've got root 2 over 2, you can rewrite that as root 2 over root 2 times root 2. And then these two are going to cancel, and so you've got 1 over root 2. So if you want to give an answer of root 2 over 2, but your only options are 1 over root 2, they're the same. Nice. How about another one? If we want the cotangent of negative 7 pi over 6, I could get into the reference angles, or what I'm going to do here is I'm just going to rewrite this in terms of sine and cosine, even though we said we don't have to. But we just started with these reference angles, so, and it's safe to just rewrite them in terms of sine and cosine. So this, if cotangent is cos over sine, yeah, cos negative 7 pi over 6 over the sine of negative 7 pi over 6. Where is it? Negative 7 pi over 6 means that I have to move clockwise, right, to 7 pi over 6. 6 pi over 6 puts me at the halfway mark, right, because that would just be pi, right? And then so 7 pi over 6 means I've moved a reference angle of pi over 6 into the second quadrant from the clockwise direction. Should probably just draw it out. Let's see if it'll make a circle. Nice. So here, oops. Make this beautiful circle. So if we're moving from the standard position, right, to this point, we've got pi over 6 or negative, 6 pi over 6. And then we wanted to move to 7 pi over 6. So let's just put that point here. Negative 7 pi over 6. Which means that this distance here is pi over 6. Negative, but I'm ignoring that because I'm keeping track of which quadrant I'm in. So now, from your unit circle, your handout, right, we know that we're at negative root 3 over 2 and 1 over 2. And so this point is at negative root 3 over 2. and 1 over 2. Right? In terms of sine and cosine, then our cos is going to be the negative root 3 over 2, and our sine is going to be 1 over 2. Negative root 3 over 2, and our sine is 1 over 2. So one way or another, you'll probably want to have some sort of unit circle on your formula sheet. Otherwise, it's really hard. So here we've got a fraction dividing a fraction, and so we can rewrite this as negative root 3 over 2 times flip and multiply 2 over 1. Oh, hello. So these 2's are going to cancel, and we're just left with negative root 3, which is our exact answer. Any questions about that one? No? Okay. Yes.
So for the question A, the reason we only did the negative root 2 over 2
Mm-hmm.
because it only had sine, right?
Yeah, because it's 1 over sine, whereas here we've got cos over sine. Nice. Cool, cool, cool. All right. Let's do another example, but a little bit different. Find all angles which satisfy tan theta is equal to root 3. Find all angles which satisfy tan theta equals root 3. Okay, so from your handout, right, if you've got root 3 for tan theta, then you know that theta is going to be pi over 3 or some multiple of pi over 3. Right? And so from our table of common values, we see that the tan, we see that. Tan of pi over 3 equals root 3. So we know I know, but he's teaching business, which is probably way more fun. Or not, depending on what you're what you're into. Like it's because you love math so much. Yeah. So we know that the solutions are going to have a reference angle of pi over 3. Right? So we know the solutions of tan theta equals √3 have a reference angle of pi/3. Okay, but here's the pickle, right? So tan theta, right, or tan theta. So we also know tan theta is y/x, right, or sine over cosine if you prefer, but let's just talk in terms of x's and y's, right, which is sine theta over cos theta if you prefer, right, assuming cos theta isn't 0. Yeah. Assuming x equals cos theta are not equal to 0. Okay. So we know that, okay, well, tan theta y/x is going to be positive as long as y and x have the same sign, right? And because we need a positive value because the √3 is positive. So we need a positive value for tan theta since the √3 is positive. Tan theta equals y/x. Let's just stick to y and x now. Will be positive as long as x and y have the same sign, right? Positive over a positive is going to make a positive, and a negative over a negative is also going to make a positive, right? But a negative over a positive makes a negative, and a positive over a negative makes a negative. So we'll be positive as long as x and y have the same sign. Oops. Hey, it changed my same to a line. Not cool. It wasn't that bad. Same sign. Just didn't know what to do with it, I guess. So if we're thinking about our circle, right? This is going to happen at pi/3, right? But it's also going to happen over here. Where this distance is pi/3. Because if we think about, okay, well here, x is positive, positive, positive. In the second quadrant, x is negative, but y is positive. So they're opposite signs. And down here in the third quadrant, x is negative and y is negative. And in the fourth quadrant, x is positive and y is negative. So that's why for tangent and cotangent, we have to keep an eye out in two quadrants, right? Because they're composed of sine and cosine. Yeah. So tan theta will be positive as long as x and y have the same sign. This happens in Q1 and Q3. So what we're going to end up having, right, is, well, eventually we'll end up and say, okay, well, if we can just move from this point to this point, from this point to this point, from this point to this point, right, then we'll have captured all the solutions. And the distance between here and here is just pi, right? And so now, instead of moving a distance of 2 pi, right, now we're just moving a distance of pi to each of the solutions. That's where we're going to end up. But for now, we can just treat these as individuals and say, okay, well, for here, right, I can figure out what values are going to satisfy this solution, right? So move from here, 2 pi, 2 pi, 2 pi, right, from pi over 3. Same thing from here, right? I can move 2 pi, 2 pi, 2 pi, and then I can kind of mash up those solutions and decide, hey, I only need to move a distance of pi. Ta-da! So in Q1, we have solutions of the form and remember we just said that theta, when we're trying to figure out, okay, what are the solutions, so what angles satisfy this equation, then we use our reference angle, which is pi over 3, and then just plus 2 pi k for integers k, right? For whole numbers are integers. Okay. And in Q3, oops, stats. And in Q3, we have solutions of the form well, here, if we're thinking in terms of our standard position, right, we've moved pi and then another pi over 3, that would be 4 pi over 3. So we have solutions of the form theta is 4 pi over 3 plus 2 pi k for integers k. And then what we'll just say is we can combine these into theta, and we'll just use the original reference angle. Theta is pi over 3 plus pi k for integers k. And I'll just make a note here. Recognizing we only move, oops. Half a revolution to each solution. Hey, poetry in math. In high school, there was a guy who wrote a love poem to pi. but like pi the number. And I just remember it being really funny, but I really wish I had it. But no, he wrote it. Yeah, probably. I could probably just Facebook him too. Doubt he has it, but he could probably come up with another one. Anyways, pi made me think of it. Pi. I'm sure he made mention of reference angles and things. I just remember it being really funny. All right, so cast. This way, right? Yeah, it came up. I was like, hey, I see it now. All right, so cats. Cat, cosine, all, sine, tan. Oh. Let's use cast. Otherwise I have to jump around. So what we're talking about is we can summarize which circular functions are positive in which quadrants someone's popular. But maybe turn your buzzer off. Quadrants using cast. Or, I mean, you could just memorize it. I'm going to do this one first. So on your handout, right, you could just go ahead and do the plus, negative, negative, plus negative just by kind of looking at what your values of y, x, and y are going to be, right? And then figure out, okay, well, what values are made up of this x and this y, right? And so, or down here, we've got our cos values, so that makes us C. Up here, we've got all values, an A. Here in the second quadrant, we've got our sine values, so an S. And then down here in our third quadrant, we've got our T. And if we move around in this direction, cast. Or cats, if you prefer. But then you can't move in. It is, yeah. I don't know. Or you can just memorize the all the functions. There's an idea. No, little help never hurts. So what we noticed, right, in that previous example was that any two angles that are pi units apart, right, will not only have the same reference angle, but points on their terminal sides on the unit circle are going to be reflections through the origin. Basically what happens in the first quadrant is also going to happen in the third quadrant, right? Or if you're in the second quadrant, it's going to happen in the fourth quadrant, right, across the diagonal. So any two angles that are pi units apart will not only have the same reference angle, but points on their terminal sides on the unit circle, bless you, will be reflections through the origin. Oh, come on. You've got a little illustration of that on your handout. Good. So what we're seeing here is that for tangent and cotangent, their period is going to be at most pi, right? Because we're just going to arrive at another solution. So arrive at that same point, essentially, but at a difference of pi. So it follows that the tangent and cotangent of such angles, of course, if they're defined, right, because we're dealing with x or y in the denominator, and so depending on which function we're talking about, so if one of those is 0, which can happen, it wouldn't be defined, right? But assuming it's defined, then the tangent and cotangent are going to will be the same. Which means the period of these functions is at most pi. To summarize all that, therefore, the period of tangent and cotangent is pi. You'll be pleased to know that we're not even drawing or graphing any tangent lines. We've got those asymptotes that we would have to deal with. Oh, thanks. Yeah. We can extend the first definition, 10.4, right, to circles of any radius r, of course. We can extend definition 10.4 to circles of arbitrary radius, arbitrary radius are greater than 0. Of course, we can't be dealing with a radius less than 0 because that just, what would it look like? No, you tell me, what would it look like? Nothing. I'm just curious. Another dimension. So we can extend definition 10.4 to circles of arbitrary radius as long as the radius is greater than 0. In theorem 10.9, which is on your handout. So I'll sneak it in here. Copy. Oops. Any radius r. So we've seen this for sine and cosine, right? Where we've just replaced r with, or 1 with r, from moving from the unit circle to a radius of any r. And we could also rewrite r if we wanted to as the square root of x squared plus y squared, right? Because x squared equals y squared, or x squared plus y squared equals r squared. So if x squared plus y squared equals r squared, and we had to solve for r, right, we would take the square root of both of these sides. So the square root of x squared plus y squared is r. And because it's positive, right, we have to have a positive radius. So there's no question. But we've seen this definition before, right, just with the unit circle, but now we're broadening our horizons here. So these functions we can use to solve some problems. How about, so now I snuck an example on the handout, so we're just going to work through these. It didn't copy. Copy. Paste. Oh, move it to the other side of the page break. No biggie. Okay, so we're going to use these to try to figure out, okay, what's the value of sine and cosine and tangent and whatever. But often what we'll have to do is we'll have to give all 6 circular functions, right? But as long as we know x, y, and r, we can easily give all the values of the 6 circular functions. And I think I make you do it on your assignment here. These we did last day. Yeah. you can already do all of the assignment. So here we go. I thought I made you do one of these next time. I think we do, but maybe the second one or something. Okay. Suppose the terminal side of theta, when plotted in standard position, contains the point 3, 4. Find the values of the 6 circular functions of theta. Okay. So we're going to have to find sine, cosine, tangent, cotangents, cosecant, and it's not coming, secant. It wasn't coming to me. All right. So in order to use Theorem 10.9, we need to know x, y, and r. So what we're saying is that, okay, if we've got our circle and Q is 3, 4, so 3 is positive, so positive 3, positive 4, let's say we're somewhere here. The radius, so here we've got 4 and 3. We can solve for, we can use the equation of a circle if we want, or just looking at it as if it's a right angle triangle, right? And so we know that x is, since x is 3 and y is 4, we know that x squared plus y squared equals r squared. So we've got 3 squared plus 4 squared is r squared. 9 plus 16, if we want to get picky here, 25 is r squared. And so r must be 5. Because r has to be positive, right? There's no question between the positive and negative. So now that we know x, y, and r, we can find all 6 circular functions. Now we can find all 6 circular functions. Sine of theta is y over r, which in our case is y is 4 and r is 5. Cos of theta is x over r, which is 3 over 5. Tan of theta is y over x, which is 4 over 3. And I'll just do them all in one go here. Secant of theta, and I'm just moving down the list, right, is r over x. R is 5 and x is 3. Cosecant of theta is r over y. R is 5 and y is 4. And finally, dealing with a page break here, cotangent of theta is x over y, which is 3 over 4. There, found all 6 circular functions. Not so bad. As long as you remember that all you need is x, y, and r, then you're good. Any questions about that one?
Confused why on our sheet. Like I get why we did it like that, but I'm confused why on the sheet it says it's noted by the sign of theta is equal to y.
Oh, well, so we moved away from definition 10.4 to theorem 10.9.
Can you not just, you can't use that one?
Yeah, but the first one, 10.4, is for a radius of 1. So it's the special, it's the unit circle case. Whereas you could rewrite theorem 10.9 ones with an R of 1, and you'd get to this definition. So you actually don't need, well, you don't even need these first 2 blocks on the first page, right? You can just replace them with theorem 10.9. Okay. But we were just building up to that. Cool. But yeah, it's just the first one was just the R is 1. Okay. How about the second question? Suppose theta is a quadrant 4 angle with cotangent of theta equals -4. Find the values of the 5 remaining circular functions of theta. Okay. This is where we get into, I don't know, kind of sneaky stuff, or just kind of getting lazy, I guess you could say, because we're not given values of x and y. But we know that the cotangent of theta has to be -4. So we're just going to pick convenient values of x and y that make that happen. Okay. And so we can pick convenient values of x and y, excuse me, that satisfy this criteria. As long as we remember that the cotangent of theta, from theorem 10.9, the cotangent of theta is x over y. And we were told that we have to be in quadrant 2. Or sorry, quadrant 4. Q1, Q2, Q3, and Q4. So we have to be in quadrant 4. Which means that our x is going to be positive and our y is going to be negative, right? But overall, we have to get an answer of -4. Right? And so here, we've got a positive x over a negative y. If we force x over y to equal -4, because that's what the question told us to do, we can let x be 4 and y be -1, right? And that would put us in quadrant 4. We can let x be 4 and y be -1.
So does it matter really which number you put?
It doesn't, right? So you could pick on any values as long as their fraction, right? X over y makes -4, and you're in the second, or sorry, I keep saying second, the 4th quadrant.
So could you have x negative like top?
No, because if your x is negative, right, then you're in Q2 or Q3. So you're bounded by having to be in Q4. because it's in, so here, right, we have to have a quadrant 4 angle. So we have to be in this area. Right. And those values have to make -4. Right. But I mean, you could have picked x is 8 and y is -2. That still satisfies it, right, on both accounts. But I'm just going to always pick the most simplest values. Because if we put x is 4 and y is -1 on here, it would be somewhere around here. Right. In the orange. Okay. So now we have a value for x and we have a value for y. Now all we need is a value for r. Right? Now we can solve for r. X squared plus y squared equals r squared. And so x is 4, so 4 squared plus -1 squared equals r squared. And so we get 16 plus 1 is r squared, so r must be the square root of 17. And you're just going to keep it as root 17, right? No decimals now. Okay. It took a little bit more work, but now we're back to the same situation that we had earlier in question 1, right? Where, okay, now we know x, we know y, and we know r. Now we can just compose all our 6 functions, right? And so we can now compose the 6 circular functions using x, y, and r. Sine theta, just moving through our list again, is y over r. Y we said was -1 over r, which is the square root of 17. And you can just leave it as that, right? You don't have to do anything. So that's nice. Moving on to the cos of theta. Cos of theta is x over r. X in our case is 4. Tan of theta is y over x, which is -1 over 4. Secant of theta is r over x. R over x is root 17 over 4. Cosecant of theta is r over y, root 17 over -1. I will rewrite this one as just negative root 17. If you didn't, it's fine. And finally, our cotangent of theta we know has to be -4 because that's where we started, but we'll just put it on here for completeness. So is x over y which is going to be our 4 over -1, which is -4. So a little bit of problem solving in the beginning, right? But if you're finding the 6 circular functions, then you know you're going to need an x and a y and an r, and then you can just use theorem 10.9 to construct all your 6 functions. Okay. I didn't like when things were just, oh, pick any value. How do you know which values, right? So, but just go for the easiest ones. Make sure that it satisfies the criteria, and if it does, then just stick with those, right? Like 4 and -1. Any questions about that one? Let's do another one then. Slightly different because it's secant, but same idea. Here we're just asked to find sine of theta if the secant of theta is -√5 and theta is a quadrant 2 angle. Same idea. We're given values for secant, and from there we're going to be able to find sine theta. Okay. So let's just jot down what we know. So we know that secant of theta in general from our sheet is r over x. And it has to be -√5. If it's a quadrant 2 angle, we better hope that our x can be negative, right? Because our radius can't be negative, and we have to get that negative from somewhere, right? And so, phew, if we're in quadrant 2 where x is negative, and so we've got a negative x and a positive y, right? And r is always positive. So, what convenient values would you pick? The most convenient values I can think of, or -1, right? So √5 as my radius and -1 as my x. That's the most simplest way that I can combine these to make -√5, right? And so the simplest values of r and x that I can think of are r equal to √5 and x equals -1. Since r must be positive and x is negative from Q2, right? From being in quadrant 2. Okay, nice. So now I know r, I know x, I can solve for y, right? We can solve for y. Because in my sine, right, remember the goal is to find sine theta. Sine theta is y over r. I know what r is, so now I just need to know what y is. In order to solve sine theta equals y over r, we need to find y. So x squared plus y squared equals r squared. X squared negative 1 squared plus y squared equals root 5 squared. And so we've got y squared is 5 minus 1. So y is plus or minus, or I shouldn't skip that step actually. Y is the square root of 4. And so remember that y must be the plus minus of 2, right? Or plus minus root 4. That hasn't been an issue before because we've just said, oh, well, the radius has to be positive. Non-issue, right? Now we need to figure out, okay, well, if we're in Q2, then our y has to be positive, right? And so since we are in Q2, y is positive 2, or just 2. So now we can solve for sine theta. Sine theta is y over r, which is y we said was 2 over r, which was root 5. Nice. Any questions about that one? So these are kind of fun just because as long as you're able to get to x, y, and r, then the rest is, I'd say, really quite simple. Our last question that we're going to do is very similar, right? Find the cos of theta where the tan of theta is 3 and theta is between pi and 3 pi over 2. So instead of being given a quadrant, this is essentially given a quadrant, right, between pi and 3 pi over 2. And so if we're thinking about our circle, at this point here, we're at pi. And then here at this point, we're at 3 pi over 2. Right. So we're in Q3. Which in Q3, our x is negative and our y is negative. Right, so we have to keep that in mind. And our r is always positive. So we know theta is a Q3 angle. We also know that the tan of theta is 3, And in general, the tan of theta is y over x. Our x and our y have to be negative, right? But because they're both negative, our tan equals 3 is going to be positive, and so we're fine, right? So let's pick the easiest values we can come up with, right? I'm thinking -3 over -1. Nice, right? So here we go. So if we let x be -1 and y be -3, we satisfy tan theta equals y over x is -3 over -1 equals 3. Put a little nicer check mark on there. And we're in the right quadrant, or in the third quadrant. Same idea, right? We want to find the cos of theta. Cos of theta is x over r. So we need to find r. X squared plus y squared is, keep doing that, is equal to r squared. If x is -1 squared plus y squared is -3 squared plus, I keep saying plus r squared. There we go. 1 plus 9 is 10, is r squared, so r must be plus or minus √10, but it's just going to be √10, right? Because r is always positive. Okay. So now, cos theta is x over r is going to be x was -1 over r, which is √10. We did it. Oh. So considering some of the stuff that you have been doing, I think these problems are pretty fun, right? X squared plus y squared equals r squared, yeah, right? So, any questions about those ones? Oh. The countdown's on, only 2 more sections to go. Sine and cos laws, and then you're home free. Well, until the final. Any questions though? Review. Final exam review. So I think I've got 2 days slated for final exam review. Yeah. And I'll get you guys a practice final, and we'll go through it together, and it'll be great. Cool. Yeah.
Is the final cumulative?
It is cumulative, yeah. You shouldn't have said that. Yeah. I was gonna just make it on trig. Is that what you guys want? No, I don't think so. Yeah. All right. So you've got all the tools that you need to do this assignment. Like I said, you're allowed to submit it as a group. In fact, if you're working together, I want you to submit it as a group. I don't want to see the same stuff over and over again. But yeah, it's not due till did I say Tuesday, November 26th? Is that a Tuesday? Is it? Yeah? Okay.
Yeah.
It is? Yeah. Okay, so then, yeah, so Tuesday is the 26th, yeah. Cool. All right. No questions? See you guys on Thursday or whatever day. Oh, well, not for me.
No.
Yeah, yeah, I'm like, I don't have a quiz, mate. Are you crazy? I'm not ready.